Hello everybody, it's Miss McNeely, and I'm sorry I can't be here today. Today's lesson is going to be on testing a claim about a population mean. Anytime we're doing a hypothesis test, we're going to follow the same process as we did with population proportions. In fact, every test we do is going to follow the same 5 steps, where we start with a hypothesis, we check the conditions for inference, we have to describe what kind of probability distribution or what kind of test we're performing, we do the calculations, and then we state our results. So every test we're going to do every day from this point forward is going to involve the same process. So I'm hoping that with the means it'll be just as clear as it was with the proportions. Your warm-up, or actually our outcomes for today, are basically going to be to check the conditions for inference when we're dealing with a mean, to perform the significance test, and then also relate significance tests, two-sided significance tests to confidence intervals like we did with the population proportion last class. So in your warm-up, you have some true-false statements related to alpha, beta, and power. You were supposed to have watched a video last night or the night before explaining the relationship between a type 1 error, a type 2 error, and what we call the power of a significance test. If you have not copied this chart down, I would recommend that you do it now. There's a place for it on your warm-up. If you need to pause the video to do so, go ahead, but it's really important that you understand the relationship between these 3 components. It's, the probability of a type 1 error we mentioned last time is the same as your significance level. So if you know the significance level, then you know the probability of a type 1 error. Calculating the probability of a type 2 error is not something you're expected to do in this course. It's a lot more complicated, and you have to know an alternative mean or proportion that's actually true. And so we're not actually going to calculate the probability of a type 2 error. However, if you're given beta, which is the type 2 error, you need to be able to understand its relationship to alpha and what we call power, which is just the complement of type 2 error. So our goal is always to keep the errors as small as possible, because the type 1 error, remember, is when we reject the null hypothesis when it's actually true. And a type 2 error would be when we fail to reject or ultimately accept the null hypothesis when it's false. And so the power of the test is basically the test's ability to detect those differences between an alternative and the null hypothesis. So our goal is always to keep the error small and to keep the power big. The power is related to a type 2 error, though. So there are some, there are some costs. If you want to decrease the probability of a type 1 error, for example, then it's going to increase your probability of a type 2 error and decrease the power of the function, which are both 2 negative things. So what I'd like you to do is pause the video so that you can jot down the table and then answer the true-false questions that follow. Okay, so in your warm-up, you were given 13 statements, and you were asked to determine if they were true or false. So, and I've got the table at the bottom to help you answer some of these. So in number 1, it says we can increase the power by choosing an alpha level of 5% instead of 10%. So if we choose 5 instead of 10, we're basically lowering alpha. So if we lower alpha, that brings us down to our table. So alpha is the probability of a type 1 error. If we decrease it, if we look to see how that influences our power, it actually decreases our power. And so this statement would be false. It's not going to increase power to do that. In the second statement, it says if we reduce the risk of committing a type 1 error, then the risk of a type 2 error will also decrease. Well, that's along the same lines. If I decrease a type 1 error, it's actually going to have the opposite effect on my type 2 error. It's going to increase it. So that statement is also false. If the results of an hypothesis test are significant, then we fail to reject the null hypothesis. Well, if the results are significant, that means that P is low. And when P is low, we reject the hoe. And so the statement would also be false. In number 4, if you reduce the sample size, then the power of the test will also decrease. Now, we don't have that in our table at the bottom, but remember, increasing the sample size is the best thing that we can do because it reduces the error and it improves the power. And so this is just the converse of that statement. If we reduce the sample size, then the power of the test will also decrease, and that is true. Reducing the sample size is going to have a negative effect on everything. In number 5, it says the significance level is the probability of committing a type 1 error. In fact, that is exactly how it's defined, so that is true. Alpha is our significance level. In number 6, it says if the significance level for a two-sided hypothesis test is 2%, then the matching confidence interval would have a confidence level of 98%. And we talked about this last class. If I'm doing a two-tailed test, then the area that I am highlighting here would be what we would call the rejection region. So if I'm rejecting at the 2% level, that means that I must have 1% here and 1% here, so that altogether that area adds up to 2%. Well, that is going to correspond to a 98% confidence interval. So that is true. There is a relationship between our two-sided tests and our confidence intervals. In number 7, it says a large p-value means that the results of the sample were significant compared to the null. While that is a false statement, we always want our p-value to be small so that we can reject our null hypothesis. So that is false. Okay, I kept the table here so you guys could still see it. In number 8, it says when a test concludes that you must fail to reject the null. So fail to reject means we're not rejecting the null. Then you may have committed a type 2 error. And that is what a type 2 error is. Type 2 error is when we don't reject the null hypothesis, so we're ultimately kind of accepting it, even though it may not be true. And that would be, if it's not true, that would be a type 2 error. So that is a true statement. In number 9, it says if a test rejects with an alpha level of 5%, then it must also reject at the 1% alpha level. Well, let's take a look. I'm just going to draw a normal curve here for a second. So let's say this is the 5% level. Let's call this, we're going to talk a little bit more today about what we call a rejection region. So let's say that's 5%. So 1%, let me do this in green, would be like here. So it is possible that I get a sample result that is in here, which means that it is going to be rejected at 5%, but not at 1%. An example would be like a p-value of 4%. It's less than 5, but more than 1. So let's see, this would be a false statement then. In number 10, it says you can reduce the margin of error in a confidence interval by increasing the confidence level. Well, let's think about that. Let's also take another look at a normal distribution. So let's say this is my confidence interval. So my sample value is going to be in the middle. And so that means that this distance and this distance correspond to my margin of error. So let's say this is just one standard deviation. Let's say that's a 68% confidence interval. If I want to increase my confidence level, then I am essentially, to be more certain that my value falls between the two values, so let's say that's a 95% confidence interval, you can see that it makes my interval wider. The mean or the proportion is, or my sample value is still going to be right in the center, but it does make those whiskers a little bit longer, so it does increase the margin of error. So this would be false. In number 11, it says if a test fails to reject at an alpha level of 5%, then it must fail to reject at a level of 10%. And this is kind of like the converse of the other one that we did. So, sorry, this is terrible. So let's say this is my 5% level. And let's say this is my 10% level. And so if I'm failing to reject at the 5% level, that means I could be here, right? I mean, that could be a p-value of 7%, for example, which means that I wouldn't be able to reject at the 5% level, but it would still be significant at the 10% level. So number 11 would be false as well. In number 12, it says you can reduce the margin of error in a confidence interval by increasing the sample size. Remember, increasing our sample size has the best effect on everything. It almost fixes everything. It's going to reduce our margin of error in a confidence interval. It's going to reduce our type 1 error, our type 2 error, and it's going to increase our power, which are all good things. So increasing the sample size always has a good effect on everything. So that's a true statement. And number 13, choosing a two-sided alternative over a one-sided alternative means you're more likely to fail to reject the null hypothesis. That is true. And the reason for that, let's say I'm dealing with a 5% significance level. Sorry, I'm running out of space. So if I'm doing an upper tail test, that would be 5%. But if I'm doing a two-tail test, then I'm looking at the area in both tails, which means that I'm looking now at the tail area of 2.5%. So it's going to be a little bit harder to get values that are that extreme on either side of the mean. So this is actually true. If you're going to do a two-tailed test, it's going to be harder to find a significant result. So if there is any way to determine or to construct an alternative that's either lower or higher, then you want to do a one-tailed test. But if you're really not sure which direction you expect, then a two-tailed test is going to be more appropriate. Okay, so what I would recommend is that you save this somewhere, because these are the types of questions I can see on an AP exam, certainly on an AP drill, where you really just have to understand the relationship of the type 1 and type 2 errors and power. You're not really going to be doing a lot with those calculations aside from what we did in our homework last class, but understanding those relationships is going to be really important. The next thing I'd like to do is just review inference for means. When we talk about sampling distributions of means, remember there's two different distributions that we use. We can use a normal distribution when the standard deviation of the population is known, but when it's not known, we can't use a normal distribution anymore, and we have to rely on our t distribution, which is defined by the degrees of freedom. So what I'd like you to do is pause the video for a minute, and I'd like you to try to fill in the blanks on the back of your warm-up with all of the inference about means, and you've got your answer bank. Not all of those answers will be used, but I believe none of them are repeated either. So if you could press pause and go ahead and complete the review for inference for means, and then we'll go over it in just a second. Okay. If our data comes from a simple random sample, which it should if we're going to do any kind of inference, and the sample size is sufficiently large, then we know the sampling distribution of sample means, x bar, is going to be approximately normal, and it's going to have a mean of mu, and a standard deviation of sigma, which is the population standard deviation, divided by the square root of our sample size, n. If we want to standardize x bar, because anytime we do probabilities, remember we got to change it to a z-score. So if I want to standardize x bar, remember any z-test statistic is always going to be our observation minus the mean divided by the standard deviation, which means that z is going to equal x bar minus mu divided by sigma over the square root of n. Problem is, if sigma is unknown, which it is in most cases, then we can't calculate the standard deviation for the sampling model. Instead, we have to use our estimate of the value of sigma using our sample standard deviation, which is denoted with an s sub x instead of sigma. Remember, all the Greek notation refers to our population. All of the regular alphabet letters refer to our sample size. So if I'm going to be using the sample standard deviation, then in my calculations, then it's no longer called the standard deviation of the sample mean. We call it the standard error because it's a little bit off. And the standard error formula is very similar to the standard deviation formula, except instead of doing sigma over the square root of n, we're using our sample estimate of s sub x over the square root of n. So if we replace sigma with s sub x, then the statistic has more variation and no longer has a normal distribution. So we can't use the z distribution. We can't use the standard normal curve. It has a new distribution, and that distribution is called the t distribution. T is a standardized value, just like z, and it tells us how many standardized units x is, or that should be an x bar, it just didn't show up very well. It tells us how many standardized units x bar is from the mean. The t-test statistic is calculated the same way that z is. You take your observation, you're going to divide or subtract the mean and divide by the standard error in this case. So t is equal to x bar minus mu divided by the standard error, or s sub x divided by the square root of n. The other difference is that a t-distribution doesn't have a mean and standard deviation. The parameters for a t-distribution are simply using what we call the degrees of freedom. And that relates to our sample size. So every single t-distribution is different. It's going to depend on the size of the sample. And because there's a different t statistic for every sample size, the degrees of freedom for a one sample t statistic is simply n minus 1, where n is our sample size. The t-distribution is going to be symmetric about 0 and is bell-shaped, so it's very similar to a standard normal curve, but it's going to have more variation, so the spread is going to be greater. As the degrees of freedom increases, as our sample size gets larger, then the t-distribution is going to get closer and closer and closer to the normal distribution, since s is going to get closer to sigma. because remember, the larger our sample, then the closer it is to the population. And finally, a one-sample T procedures are going to be exactly correct only when the population is normal. And it must be reasonable to assume that the population is approximately normal in order to justify the use of the T procedures. T procedures are going to be strongly influenced by outliers. Oops. So you always want to check the data first. If there's outliers or if the data is really skewed or the sample size is small, then the results, I don't know why that keeps moving, then the results are not going to be reliable. So if you're not told in the problem that the distribution or the population is normal and you have a small sample, if you're given the data, then you always want to graph it. And that's when you use your normal probability plot. And if you go back to your stat plot menu, the normal probability plot, if you look at where it has the type of graph, it's the very last one. It's the one that's underneath the histogram. So if you have data, if it's a small data set, less than 30, you want to go ahead and plot those points and see if your normal probability plot is linear. If it looks linear, then you can conclude that the data is approximately normal, and then you can continue with inference procedures. If there are a lot of outliers or if the data is clearly not normal, then it is not appropriate to continue. Okay, so let's talk about tests of significance for means. The process is the same as it was for proportion. So I'm going to go through this pretty quickly because it's really the same thing. We're just going to be referring back to our sampling distribution and the T distribution to carry out the tests. So tests of significance for means are going to follow the same process as before. We start with a statement of a hypothesis. Remember that our hypotheses are always in terms of the parameter, which is the population mean in this case. Remember too, when you're dealing with means, you always want to include units. You didn't have to do it for proportions, but you do need to make sure that you include units for your hypotheses. So we always want to define the parameter and then state our hypotheses. So remember, the null hypothesis is always that the mean is equal to some value, and it's usually the status quo. It means that there's no change or no difference. And then the alternative can be one or two-sided. So if it's less than or greater than, we say that this is one-sided. And if we're not sure what difference or if our value is going to be larger or less than, we say that this is a two-sided test, and we just use a not equal to sign. Okay, assumptions and conditions. So remember, with a mean, it's a little bit different than it was for the proportion. We still need to have randomly selected data, whether we're doing a sample or we're doing a controlled experiment. Our data has to come from random. There has to be some randomness in our data collection method. If there's any kind of bias, then we really don't want to continue with inference. Just like it was with the proportion, if I'm sampling without replacement, then we want to make sure our population is at least 10 times our sample size. So if I'm dealing with an infinite process, I don't really have to list this condition. So like if I'm dealing with a production line of things where it's an infinite, like I'm producing cereal boxes, and I know I'm just going to keep producing cereal boxes, it's not as big a deal about sampling without replacement. But if I'm dealing with a finite population and I'm sampling without replacement, then I want to make sure that I list this condition. As a general rule, it's always safe to list it, and that way you don't have to worry about losing points for getting it, or for forgetting it. Instead of looking at the number of successes and failures as we did with a population proportion where we had to do n and p and n times 1 minus p, when we talk about having a large sample, either our population is normal or our sample is larger than 30. If that information is not provided to you, for example, if the problem doesn't state that the population is normal and you're dealing with a small sample and you don't have the data, then you're going to want to write on your paper, assume SRS. So even if it's not stated in the problem, the only way you can continue with inference is if you make the assumption that the data is coming from a simple random sample. And so you usually want to do that. If it states in the problem, you can just write SRS, and then put a check mark, maybe circle the word SRS or random in the problem so it's clear that you verified that. If it doesn't say that it's normal and you have a large sample, so for example, let's say n is equal to 150, you can say n equals 150, which is greater than 30, and so the condition is met there in terms of normal. if you're given the data and it doesn't say anything about the population being normal, then that's, again, when you want to do that normal probability plot. And just sketch the graph. You don't have to scale it or anything. Just do a quick sketch and then just say, since the normal probability plot appears normal, we can assume that the data is approximately normal, and then continue. Make sure you use the word approximate, because sometimes the graders can be finicky about that. And then tests of significance. So we talked when we were dealing with distributions for sample means, we talked about the different cases where sometimes the standard deviation of the population is known and sometimes it's not known. And it really is more reasonable for the standard deviation not to be known. But you may have cases where there is some data on the standard deviation. So that determines which type of test or which type of distribution we're going to use. Because in step 3, if you're going to be doing it by hand, then you want to make sure that you state the probability distribution and the parameters. So you're going to be using a normal distribution if sigma is known and a t-distribution if it's not known. And just like before in our last class, I'm going to also show you how you can do both of these tests on the calculator. So if sigma is known, then you're going to be doing what we call a t-test, and you might actually want to just go ahead and get in the habit of saying it's a one-sample t-test, or if sigma is unknown, you would say it's a one-sample t-test, because in the next chapter we're going to be looking at comparing two samples or two populations. Okay. And then when we're carrying out the test, remember, this just kind of, I showed you this graphic when we were dealing with proportions, so I figured I'd kind of show you the same thing. When you're actually completing the statement about probability, if you're doing an upper tail test, this is when you're going to say, the probability of x bar is greater than some value, and either the probability of z is greater, or you'd say the probability of t is greater. If you're doing this on the calculator will give you those two test statistics. If you're doing a lower tail probability, then make sure that when you're writing all the probability statements on your paper, now we're using x bar and not p hat. And so if you're doing a lower tail test, you're going to do x bar is less than, and that means your z is going to be less, your t is going to be less. If you're doing a two-tail test, this is a little bit more complicated when you're writing it down, only because the direction of your inequality is going to depend on your sample result. So if your sample result is more than the null hypothesis, you'll use a greater than symbol, but you always want to make sure you're doing 2 times the probability that x bar is greater than whatever your sample result is, or 2 times the probability that x bar is less if the sample result is less than your claim. Now when the calculator is doing the calculations, if you're using the test on the calculator, it will report the p-value and it will already be doubled. But if you are calculating the probability by hand, you will have to remember to double it. And so that is just a little nuance that sometimes students forget to do when they're performing a two-tailed test. So there's an example like that today, so I'll make sure that I go over that. Step 4 and step 5. So step 4 just goes about the calculations. For the sake of argument, we assume that the null hypothesis is true, and then we determine the probability of attaining the sample result x bar, and then figuring out, what's the likelihood that it is as extreme as it is, given that the null hypothesis is true. And if it's really, really unusual, then that gives me evidence to reject the claim. So if p is low, we reject the hoe. And then finally, when you're interpreting your result, same as before, 3 questions you want to answer. Is the result significant? Can we reject the null hypothesis? And then explain what all that means in the context of the problem. All right, so let's just get through some examples to give you a sense of what this is going to look like when we lay it all out. I'm going to do example 1 with you, and then I'm going to help you set up number 2, and then expect you to finish it on your own. So in number 1, it says a coffee vending machine dispenses coffee into paper cup. You're supposed to get 10 ounces of coffee, but the amount varies slightly from cup to cup following a normal distribution. So that's important, right? Normal distribution, we're supposed to get 10 ounces of coffee. Assume it's known that the standard deviation of the amount of coffee dispensed into each cup is 1 ounce. So since that's referring to the population, I know that's sigma. And that's going to be important because that's going to help me determine what kind of test I'm going to do. It says here are the amounts measured in a random sample of 20 cups. So that 20 cups, that's going to be our N, and this is important that we have our random sample because that's going to go with our conditions. In this case, you're given the data. So I'm going to go ahead and just go into one of my lists and go ahead and type this data in. I'm actually going to pause so you don't have to watch me do that. Okay, so I've got all my data in. There should be 20 values. And we want to know, is there evidence that the machine is shortchanging customers? Well, let's start with the claim. The company says that there should be 10 ounces of coffee in each of the cups. So when I state my null hypothesis, remember, this time we're dealing with a mean. So that's one of the things that I know some of you are still finding challenging, is knowing the difference between whether it's a proportion problem or a mean problem. One of the dead giveaways is when you see units, that's going to be an indication that you're dealing with a mean. So our null hypothesis is going to be that the mean is equal to 10 ounces. And again, with mean, you have to include the units. The alternative, we're looking to see if they're being shortchanged. So we want to see if the mean is less than 10 ounces. In the first step, again, we have to define our parameter. So we'd say the mean would be, or mu would be the mean number of ounces dispensed. And I'm just going to jot down some of the other information I know. I know, for example, that sigma is equal to 1 ounce. And I guess that's about it, because we're given the data. So the next step would be to check our conditions. So the first thing I want to look at is it an SRS? Yes, it is. Now, our sample is small. We only have 20 cups in our sample. However, the population is normal. And so the second condition is met. And finally, this is where we're talking about sampling without replacement and looking to see if our population is at least 10 times n. Well, in this case, it's an infinite population, but I'm going to go ahead and just write population is greater than 10 times 20 or 200 cups. We can assume that is true. Okay. Now I've got to think about what my next step is going to be. I know most of you are just going to go ahead and use the calculator to do this, so I'm going to do it with a calculator and show you how to perform the test there. Because the standard deviation is known, I know that I can use a z-test. Now on the calculator, if you go to your stat menu and go over to tests, you'll see that the first two options are z-test and t-test. That implies that we're dealing with a one sample z-test is what we're going to do here, since the standard deviation is known. In the next chapter, we'll be looking at those two sample z and t-tests, because we'll be comparing two populations. So in this case, we're going to go ahead and do a z-test. Because I have the data, I'm going to go ahead and choose that option where it has the mu 0. That is basically referring to your null hypothesis. In this case, my null hypothesis claims that there are 10 ounces in each cup. The standard deviation is also given, and that is 1 ounce. The data is in list 1 with a frequency of 1. Now, if you had a frequency table where you had outcomes in list 1 and then the frequencies in list 2, that's how you would enter in the frequencies. And then the second to last line is just referring to your alternative hypothesis. So we're claiming that the true mean is actually less than the claim, or less than mu sub 0, and so that's going to be the second option. And we can go ahead and have the calculator calculate. Now, everything I need to write out my calculations is here. It's a probability calculation, so let's use proper notation. The sample statistic in this case is now x bar instead of p hat. Because my alternative is claiming that it is less than 10 ounces, I'm going to use a less than sign in my probability calculation. X bar has been calculated for me as 9.845. And then again, since I'm using a z-test, I want to make sure that I translate this into a z-test statistic, which is also given to me. It's negative 0.693. And in this case, the p-value is just 0.244. Okay. And so clearly that value is not significant. It's not less than 5% at least. And so because it's not significant, so what we can say is since 0.244 is greater than 0.05, the result is not significant. And remember, if it's not significant, we cannot reject the null hypothesis. And now we want to write this in terms of the context of the problem. If I can't reject the null hypothesis, that means that I can't prove that the machine is shortchanging customers, or that the mean amount dispensed is less than 10 ounces. And so you can explain that any way you want, as long as it's in the context of the problem and it's correct. So we do not have evidence to conclude the mean, what is it, coffee that we're dispensing? Yeah. We can't conclude that it's less than 10 ounces. So if you want to say also customers are not being shortchanged, you could. Oops, my computer froze.